that means when we talk about forces in two directions, it means forces being applied at an angle of some kind, which is very similar to how we solved launched projectiles, right? We have to break things into their X and their Y components. The great news is that we already know how to do that, okay? We already know how to break things into X and Y components. We already know that to put numbers into an equation, whether it's a projectile equation or a net force equation, we have to be X and Y separate, okay? So the best way for these are, we're just going to kind of jump right in here with practice, okay? We're going to get good at drawing the diagrams for these problems because the diagrams are super, super important. What are those diagrams called? Free body diagrams, okay? So we're going to get good at drawing those here, all right? We're going to look at an example that says a force of 2,000 newtons acting at an angle of 60 degrees with respect to the horizontal is exerted on a towed car. The car is accelerated from rest at a rate of 10 meters per second. Find the mass of the car. Okay, so let's start with the diagram. Okay, remember we just start with the dot. Okay, we've got a force being applied 60 degrees to the horizontal. So all that means is that we're going to draw our angle just like that. Right? To the horizontal means I'm coming up 60 degrees from the horizontal X, the positive X axis. And so mine is really not drawn to scale there, right? 60 degrees should have a little steeper slope, but it's close enough, okay? Then we've got, it doesn't mention anything to us about acceleration. So it doesn't mention anything to us about friction. So I leave that off. But if I'm dealing with a car, do I have gravity? Yes, right? I always have gravity, and I'm on a surface of some sort. So I've got the normal force. Do you remember that being called the normal force? It's from the surface and it's going upward. Okay? This force that's pulling on the car, we can either call it the force of tension, we can call it the applied force. There's really not a big concern as to what the name of that force is, but we know that diagonal force has a value of 2,000 newtons. Okay, so do you see how the diagram is drawn? Right, drawing that is super, super, super important. So this side of that component of my force right here, I might call force of tension in the Y direction. This one I might call force of tension in the X direction, right? I need the components of that force. I do not want to plug in 2,000 into my equation anywhere because that force is at an angle. I have to have the components of it. So I want you to just, before we do any more work than that, I want to look at what the question's asking for, okay? The car is accelerated at a rate of 10 meters per second squared. Find the mass of the car. So is this acceleration we're talking about here, do you think the acceleration is horizontal or vertical? Horizontal, right? A towed car is pulled, but it moves horizontally, right? So we're dealing with X values here, which means we're really only concerned about what's happening in the X direction. All right, so if I was going to set up my net force equation, I would take my positive X forces minus my negative X forces. Do I have any horizontal forces that are going toward the left? No, because it didn't give me any indication of friction, so I'm just going to leave that out. Okay, I could write in a -0 just to tell myself that I thought about those leftward forces, but I don't necessarily have to. Okay, so this right here is called the net force equation, and we always take positive forces minus negative forces, right? Anything that's going in the positive direction horizontally minus anything that's going in the negative direction horizontally, okay? And if you want to put a little X on there so you know you're dealing just with the X direction, you could do that as well. Uh-huh.
So FTX is your Fnet.
Mm-hmm.
Can't you just find FTX and then divide by 10?
Yep, bingo. Yep. So that's the whole reason we're setting up this equation. So let's go back up here and solve for what FTX is, right? We're going to use cosine. So FTX would be 2,000 times cosine of 60. 2,000 cosine 60 gives me, 1,000. And so then I'd come and plug that in. 1,000 equals, and then what can I substitute for F net? I can take mass times acceleration. And so I get a mass of only 100 kilograms. Okay, there's two ways that we solve for the net force. The first of which is the net force equation, right? Setting up positives minus negatives. The second one is to take F net equals MA. And we do that substitution a lot. A lot. That gets substituted in there. Okay? A Newton is equal to 1 kilogram times meters per second squared. Right? That's what a Newton is. 1 Newton is equal to that. So it's derived from the equation mass times acceleration, right? That's where that comes from, is using those units. So that's how we are able to cancel them out. Okay, kilograms times meters per second squared. So when we divide that by meters per second squared, it leaves us with kilograms. Okay, so our object or our diagram here looks pretty similar, actually. Actually, let me draw it a little bit bigger. Okay, we've got a force being applied here, 200 newtons. And we've always got gravity. And it says it's sliding. So although it's being lifted, it's attempted to be lifted, it's not off the surface yet. So we still have a normal force. Okay? I don't know how it's being lifted, so I'm just going to call this an applied force. So I would call this F applied Y and F applied X, right? You can label those however you want. Gosh dang it, I'm sorry, I didn't realize that was so hard to see. My bad. All right. Sorry about that. Okay. So it's asking us for the normal force, okay? And so is that a horizontal? That's a vertical force. I'm going to set up my net force equation with only vertical forces. So how many vertical forces do I have? 1, 2, and 3, right? I've got 3 total vertical forces because the y component of that applied force is still a vertical force, right? The vertical component, I still count that. So I've got 2 of them that are going upward, the normal force plus force applied y. And then what's my downward force? My gravitational force, okay? So I put in all, right? Net means the sum of all of them. So I'm going to put all of those into that equation, okay? Any questions about how that is built? Okay, now, since it says it begins to slide, is my object moving in the vertical direction at all? So what does my net force have to be in the y direction? Right? My net vertical force has to be 0, right? It's not even moving, let alone accelerating, right? Vertically, this object is at rest. And so my net would be 0. My normal force is what I am solving for. So I'm going to just leave that there. F applied y, I can solve that right here, right? I would say F applied y is equal to 200 times sine of 40, right? If you don't have your calculator out, please have that out so we can get these things solved. So my applied y, I got a value of about 128.6. All right, so I'm going to plug that in right here for F applied y, 128.6. And then how do I always solve for Fg? How can I always solve for the weight of an object? Or the force of gravity, right? Same thing. Fg equals what? Mass times gravity. The weight, or the force due to gravity, is always equal to mass times gravity. And what is gravity on the Earth? 9.8. So that means to find FG, we take mass times 9.8. And I get a value of 490 newtons. So that's going to be what gets plugged in right here. An 84 kilogram sled is being pulled with a force of 40 newtons at an angle of 33 degrees from the horizontal. It asks me what is the normal force and what is the horizontal acceleration. So it asks me two different questions. Can I solve those in the same equation? Can I solve for these two different things in the same equation? No, because one is vertical and one is horizontal, right? So let's start with our diagram here. Our diagrams look pretty similar, right? We've got always gravity. We've got an applied force here at an angle. So 40 newtons at 33 degrees. And then we've got a normal force because it's still on the surface, right? It's on the ground. It doesn't include anything about friction yet, right? We'll get to that, but not yet. So I'm just going to label these as F applied. It could be a pull. You can label it what. I just like to use applied because it's kind of a general, like generic name for a force I'm unsure of, right? An applied force. We can decide which of those ones we want to solve for first. It makes no difference, but we're going to have to do them separately. So let's just solve for the normal force first, because that's what it asks for first, okay? Do you think I'm going to need both F applied Y and F applied X for my problem at some point? Yeah, so let's go ahead and solve for those so that we have both values. All right, F applied X, we would use cosine. Can you guys still see that okay? Okay. 40 cosine 33, and then for Y, I would use sine. Now we've got our values for applied Y and for applied X, 33.5. So we would never use our 40 in our equation ever, right? Once we break that into its components, we'll not use that anywhere. Okay, if we're wanting to solve for the normal force, we need to use our vertical forces. So there's 1, there's 2, there's 3. All right, we're going to use all 3 of those. So in our net force equation, F net in the Y direction, can you see that blue okay? F net in the Y direction would be what upward forces do we have? Normal, applied Y, and then what downward force do we have? Gravity, right? FG. Okay, so then I can start looking at plugging in my numbers. Is my object moving in the vertical direction? Is it accelerating in the vertical direction? Right, it's a sled, so it's being pulled. Is it accelerating in the vertical direction? No, so my net force is 0. My normal force is what I'm solving for. Applied Y is 21.8. And FG, I can just plug in mass times gravity, right? I can do that separately, or I can just plug it in right there. But if I'm going to solve for FG, I would take 84 times 9.8, right? Do we feel pretty comfortable with calculating weight like pretty quickly? That's something that we're going to have to be able to do a lot. So that's something that it's got to be kind of a second nature for us, is being able to find weight or FG. Okay, so I got about 823.2. All right, and then I'm going to solve for my normal force. That's not what I had. No. I had 801.4 newtons. Okay, so here's how we solve that, right? We're going to add these two together, 21.8 minus 823.2, but then that has to be moved to the other side. Our normal force should never come out negative, right? We can't have a negative normal force because our force is going upward. So we cannot have a negative normal force. If we had a negative normal force, that would mean that our object is not on the surface anymore. So that's not good. Okay, so there is our value for normal force. Now for our horizontal acceleration. Horizontal acceleration, I need to use my horizontal forces, which I think I just have one of. So I'm going to say F net in the x direction is equal to F applied x. Right? So F applied x is 33.5. And then what can I substitute in right here for the net force? M times A. So 84 times the acceleration, right? The net force. The other way to solve for net is F net equals MA. So I'm going to substitute that in right there. Mass times acceleration. So I'll take 33.5 divided by 84. And I get an acceleration of 0.399 meters per second squared. Any questions about that? Okay. All right, we're going to stop